Hello people, welcome to Gurukula. I am Jai. So today in this video we are going to see about the free space path loss model. So this video is going to have two parts. So in the first part we will be seeing the formulation of the Free's equation, and in the later part of the video we will be seeing how the Free's equation is used for modulating the path loss model. So without any further delay, let's get into today's video. And as usual, if you like this video, do press the like button. If you unlike it, press the unlike button so that I'll consider that as feedback. And if you have not yet subscribed, please consider subscribing to this channel. So by setting up the environment, so first of all, to start off with, we have to define certain variables in order to take it further our derivations. So I will set up the environment first. So here we are going to consider a transmitting antenna, and then we are going to consider a receiving antenna over here, and we are also going to assume that the transmitting antenna is going to have the power of PT, and the gain of the transmitting antenna will be represented by GT, and similarly the power at the receiving antenna will be represented by PR, and the gain of the receiving antenna will be represented by GR, and the distance between the transmitting antenna and then the receiving antenna is represented by D. So these are all the various variables which we have to define as in first stage to continue our derivations. So PT stands for it's a power applied to the transmitting antenna, and GT represents the gain of the transmitting antenna, and PR represents the power received at the receiving antenna, GR represents the gain of receiving antenna, and D represents the distance between the transmitter and receiving antenna, and sometimes in some literature it will be represented as transmitter receiver separation as well. And in addition to these variables, so we are also going to have certain assumptions over here. The first assumption which I am going to make here is I am going to consider that the antennas are lossless. So if I say that antennas are lossless, I am going to consider both the antennas, the transmitting antenna and then the receiving antenna is both considered to be a lossless antenna, so whatever the power that I am applying over here, the same power is going to be radiated from the transmitting antenna. So that is what I mean by the lossless antennas. So any loss that is observed in the transmitter side is considered to be 0, which means I am going to consider the lossless antenna, which means my signal is not going to get attenuated in any aspect. So that is the first assumption which I make as an initial stage, and later on we will be considering all the parameters once we have formed particular equations. The second assumption what I am going to make here is I am going to consider the antennas are isotropic. So you very well know what isotropic antennas are. So the isotropic antenna is going to radiate an equal gain irrespective to the direction. So this is the radiation pattern for an isotropic radiator. You could see that it has an spherical radiation pattern, and the gain is going to be constant, which means it will going to give an unit gain in all the directions wherever it is placed. So that is the second assumption whatever I have taken. And one more assumption is we have considered that there is no obstacles between the transmitter and then the receiver. As the name says, we are going to formulate free space propagation environment. I have not considered any obstacles in between transmitter and then the receiver. So obviously we are going to consider only the line of sight signal, and we are not considering any of the multipath components over here. And of course this model will be well suited for communications such as satellite communications, where you will have only line of sight and the reflecting signals will not be there in that particular thing. So the free space propagation model is more suited for modeling the satellite communication kind of environments. So the main aim of this particular derivation, we are going to march towards finding the value of the amount of signal that can be effectively received at the receiver end. So this value, so this PR, that is the amount of received power at the receiving antenna, so we are going to derive towards finding the value of PR. So in order to identify or in order to calculate what is the maximum amount of power that I could receive at the receiver side, first I should know what amount of power that I have transmitted at the transmitter side. So first of all we will start observing from the transmitter side. So transmitter side, what could be the power that I have transmitted is defined by using the term we call it as power density. So when I say power density, so power density is the measure of amount of power per unit volume. So I will take PD as the power density, and that is defined by, mathematically it is represented as power received over surface area. So here when I am talking about the power received, I am talking from the transmitter side. So I am going to consider only the transmitting antenna, and we know that the amount of power that is fed to the transmitter by the feed line is what we have considered as PT. And then the surface area, here I am going to consider the surface area as sphere, because we have assumed that the antennas are isotropic, so that the isotropic antenna will have a spherical radiation pattern, so that the area of sphere is 4 pi d squared. So that I will get the power density equation like this. So PD is equals to PT, which is actual power that I fed to the transmitting antenna, over surface area, that is 4 pi d squared, which is area of sphere. And we all know that this equation is valid only for the isotropic antenna. We have made an assumption that we are using isotropic antennas, but in real time situations we are not going to use isotropic antennas, so that we'll be using directional antennas. So what do you mean by directional antennas? The gain of that particular antenna will be higher in one particular direction. So in other words, what I could say is it will not have the unit gain. So we cannot take that the gain value is equals to 1 anymore. So that we will try to slightly remodify the above equation, the power density equation, considering the unit gain. So when you consider this particular radiation pattern, this is the radiation pattern for dipole antenna. So you could see that the gain of this particular dipole antenna is maximum in these two directions, and the gain is very minimum or even zero on this particular directions. So it is very much important to consider the gain of the particular antenna when we are talking about directional antennas. So when I rewrite the power density equation by considering the gain of the transmitting antenna, I will get that the power density is equals to PT over 4 pi d squared times GT. So where GT represents the gain of the transmitting antenna. So now I have decided that this is the maximum power, or the power which I am going to transmit from the transmitter side. So that is all about we have to observe from the transmitter side. So once we know the power that we transmitted from the transmitter side, we could happily derive what will be the received power at the receiver end. So now we will start observing the equation from the receiver side. So receiver will receive the signals effectively based on a particular term, we call it as effective aperture. So receiving antennas receiving capability will greatly decided by the effective aperture of an antenna. So when I say effective aperture in antenna theory, so it is the measure of how effectively an antenna is receiving the radiated power. So that is denoted by the letter AE, that is effective aperture, and it is mathematically defined by the power received over the power density, which means the transmitted power. So here the power received, now we are talking from the perspective of receiver side, so that the power received at the receiving antenna is what we defined as PR. So the effective aperture can be defined by AE is equals to PR over PD. PD stands for the power density, that means the transmitted power, which we have already calculated over here. So now I will try to slightly modify this particular equation. Since I am marching towards finding out the value of this PR, I will try to slightly modify this equation so that I will get PR is equals to PD times AE. So now I know the value for the PD, which I have already calculated over here. So now by substituting the value of this speed, this power density over here, my equation will be like PT GT over 4 pi d squared times AE. So now it is very much important to define or to write effective aperture in relation with gain and then the size of the antenna, so that the effective aperture will be reflected in the size of the antenna and as well as the gain of the particular antenna. So it will be very much useful, and it will be very much reasonable if we represents this effective aperture in terms of gain and then the wavelength. So the relation between the effective aperture and then the gain can be given as lambda squared over 4 pi times g, where the lambda represents the wavelength, and you all know that the formula for wavelength is c by f, where f is the frequency and which the wavelength will define the size of an antenna. And you could observe from this equation that your effective aperture is directly proportional to the gain of the antenna. So if I increase the effective aperture, the gain is also going to get increased, and the vice versa is also possible over here. So now I know the value for effective aperture in terms of wavelength and then the gain. So now by replacing this particular value in my equation, received power equation, I'll get PTGT over 4 pi d squared. So this is for the power density, and this lambda squared divided by 4 pi times gr, and this is for my effective aperture. So now I will try to slightly rearrange all the terms like this. So now I got, so PR, the amount of power that I received from the receiver side is equals to PT GT times GR into lambda squared over 4 pi d the whole squared times L. So here I have considered the losses as well. So since the loss and then the power received is inversely proportional, I have included the loss factor in the denominator side. So when the loss is getting increased, and obviously my received power is going to get decreased. So that is the reason why the loss is included at the denominator side. And now this fancy equation is what we call it as Frei's free space equation. So this free space equation will play an vital role in formulating the path loss model, which means the free space path loss model, in our later videos. So this video will represents the formulation of the Frei's free space equations. So we will take this Frei's free space equation and we will try to observe certain things which the Frei's free space equation tells us. So considering the Frei's free space equation, you know what are all the terms that is written over here, the variables PT, GT, GR, the lambda squared. Lambda is nothing but the wavelength, and the L that is represented over here is the loss, and D is nothing but the distance between the transmitter and then the receiver. So there are certain inferences which we could observe from this equation. So first one is, so the received power decays at the rate of square of distance between the antenna. So when we consider this PR, I will come to this D later on. So this PR is the received power, and you could see that the received power is inversely proportional to D squared. So which we could conclude that the received power will decay at the rate of square of distance between the antennas, which means the transmitter and then the receiving antennas. And the second inference what we could take is, the received power is represented as a function of distance between transmitter and then the receiver. Since this particular D factor, which means the distance between the transmitter and the receiver, greatly defines the amount of power received at the receiver side, we should represent the Frei's equation as a function of distance between transmitter and then the receiver. So that's the reason why we have written PR of D. And you could see these particular terms PT, GT. So these two terms, the product of transmitted power and then the transmitted gain, is what we refer to as effective isotropic radiated power. We often used to abbreviate that as EIRP. So EIRP is nothing but the maximum power that is radiated, and it is compared with isotropic radiation. And the unit for this particular thing is dBi, which is nothing but dB gain with respect to isotropic antenna. And sometimes we will not be using isotropic radiator in practical situations, and instead we will be using an half wave dipole antenna. In such cases, we will be taking ERP, which means effective radiated power, instead of effective isotropic radiated power. So if you consider effective radiated power, the power is radiated will be compared to half wave dipole antenna instead of isotropic antenna, then the unit will be dBd, which means dB gain with respect to dipole antenna. So these are the various inferences which we could get from the Frei's equation. And also you could see that the received power is directly proportional to the terms transmitted power, transmitting antenna gain, and the receiving antenna gain. So whenever these terms are increased, the gain of transmitting receiving antenna or the power of the transmitting antenna, then you could achieve the increase in the received power. And at the same way, when you increase the distance or when you increase the loss between the transmitting and then the receiving antenna, and your receiving antenna power will fall down. And also it is somewhat related to the size of the antenna as well. Lambda is the wavelength, and the wavelength will contribute in the size of the antenna design as well. So the size of the antenna is also considered in writing the PR equations. So that's all about in this particular video. So in order to sum up this particular video, we have tried to observe the formulation of Freie's free space equation in two factors. The first of all, we started off from the transmitter side. So in transmitter side, we just define the power density of isotropic antenna, and then in most of the practical situations we might have the non-isotropic antenna, so that we have to consider the gain factor as well, so that we redefine the total power transmitted at the transmitter side including the gain factor. So this is all about the transmitter side. And coming to the receiver side, we just defined what will be the received power by considering the effective aperture, and we just stated how effective aperture can be represented in terms of lambda and then the gain. And finally we derived the equations PR is equals to PTGTGR into lambda squared divided by 4 pi d squared times L. And so this particular equation is what we call it as Freie's free space equation. So that's the end of the video. The remaining thing, which means the second part of this video, will cover how do we formulate path loss model, free space path loss model, by considering this Freie's free space equation into account. So that will be the second part of this particular video, and the link is given in the top right corner. You can check out the video of this. So do consider subscribing to this particular channel. So until then, happy learning. See you.